I'm showing you a table that summarizes the results of a binary classification model. It shows how many instances were correctly and incorrectly classified. Specifically, it shows true positives, correctly predicted positive cases, true negatives, correctly predicted negative cases, false positives, incorrectly predicted positive cases, and false negatives, incorrectly predicted negative cases. This column shows the number of instances the model predicted to belong to class 0, negative class. This column shows the number of instances the model predicted to belong to class 1, positive class. This row represents the actual class labels of the instances which actually belong to class 0, negative class. This row represents the actual class labels of the instances which actually belong to class 1, positive class. This is the number of true negatives. The model correctly predicted 90 instances as belonging to class 0. This is the number of false positives. The model incorrectly predicted 10 instances as belonging to class 1 when they actually belonged to class 0. This is the number of false negatives. The model incorrectly predicted 20 instances as belonging to class 0 when they actually belonged to class 1. This is the number of true positives. The model correctly predicted 80 instances as belonging to class 1. Before looking at the model's predictions, I knew there was a 20% chance that a randomly selected instance belongs to class 1, positive class. This is one of the multiple choice options. I will check if this is correct after calculating likelihood ratios. This is another multiple choice option. I will check if this is correct after calculating likelihood ratios. This option presents a relationship between likelihood ratios and sensitivity, specificity. I need to verify this formula. LR1 and LR0 are likelihood ratios for class 1 and 0 respectively. Sensitivity and specificity are metrics related to the performance of the binary classification model. This option states a relationship between likelihood ratios LR0 and LR1. I need to verify if this holds true. These are the formulas for calculating sensitivity and specificity. TP stands for true positives, FN for false negatives, TN for true negatives, and FP for false positives. I'll use these formulas and the confusion matrix to calculate the values for sensitivity and specificity. This is the overall theme of the problem. We're assessing a model designed to separate data into two categories, binary classification. Let's figure out how good this model is. Okay, the goal here is clear. We're evaluating a model using a specific function in a confusion matrix. Let's break it down. I'll use this table to calculate the sensitivity and specificity of the binary classification model. Sensitivity tells us how well the model identifies positive cases, while specificity shows how well it identifies negative cases. Both are crucial for evaluating the model's performance. I'll use the counts of true positives, true negatives, false positives, and false negatives from this confusion matrix in my calculations. Let's get calculating. This equation shows the relationship between the likelihood ratios, LR1 and LR0, and the model's sensitivity and specificity. LR1, the likelihood ratio for class 1, positive class, is the ratio of the probability of a positive test result given a positive class to the probability of a positive test result given a negative class. Similarly, LR0 represents the ratio for the negative class. This equation proves to be very useful in understanding how the model's performance metrics influence the likelihood ratios. It's a key insight. This statement is incorrect. Based on my calculations using the confusion matrix, I find that LR1 is actually approximately 8, not 4. Oops, we got that wrong. This option is also incorrect. My calculations from the confusion matrix show that LR0 is approximately 0.22, not 0.25. Not quite right, let's review this. This column represents the number of instances the model incorrectly predicted as belonging to class 0, negative class. That is false negatives and true negatives. It is a part of the confusion matrix that helps in evaluating model performance. This row indicates the actual number of instances belonging to class 1, positive class. I use this information, along with the model's predictions, to calculate the performance metrics such as sensitivity and specificity. Similar to the previous one, this row represents the actual instances belonging to class 0, negative class. This is essential for calculating specificity. This is the overall problem we are tackling. We are using a binary classification model, meaning the model predicts one of two classes, 0 or 1. I need to evaluate its performance using metrics like likelihood ratios, sensitivity, and specificity. This is the main objective. This is the overarching goal for this exercise. We're working with a binary classification model, meaning it outputs one of two possible classifications, 0 or 1. My job is to assess this model's performance, and that's what this whole exercise is about. Let's do it. I'll use this to calculate sensitivity and specificity, which are crucial for calculating likelihood ratios. The matrix shows the counts of true positives, true negatives, false positives, and false negatives from a binary classification model. This column represents the number of instances the model predicted as belonging to class 0, negative class. This column represents the number of instances the model predicted as belonging to class 1, positive class. This row shows the actual class labels for instances that truly belong to class 0. This row shows the actual class labels for instances that truly belong to class 1. This is the number of true negatives, instances correctly classified as class 0. This is the number of false positives, instances incorrectly classified as class 1. This is the number of false negatives, instances incorrectly classified as class 0. This is the number of true positives, instances correctly classified as class 1. This section presents 4 statements about likelihood ratios, LRs, calculated from the confusion matrix, for me to assess. Let's see if I can get them all right. Statement A claims that the likelihood ratio for class 0 is approximately 0.25. I'll calculate this value later to check this statement. Statement B claims that the likelihood ratio for class 1 is approximately 4. Let's calculate LR1 to verify this. Statement C says that the ratio of LR1 to LR0 equals the sensitivity divided by 1 minus the specificity. I'll check this relationship after calculating the required values. Statement D states that the product of LR0 and LR1 equals 1. I'll compute LR0 and LR1 to verify this. This one is tricky. I'm evaluating a binary classification model's performance using the given data. Binary classification means the model predicts one of two classes. This introduces the problem. Using a confusion matrix and the prior probability of class 1, P1, equals 0.2. Assess the correctness of the multiple-choice question statements. The prior probability is the overall probability that an instance belongs to class 1 before any prediction is made. I'm showing you the confusion matrix. It's a table that summarizes the performance of a binary classification model. You see the counts of true positives, 80, true negatives, 90, false positives, 10, and false negatives, 20. We'll use these numbers to calculate some important metrics. I'm calculating sensitivity. It's the proportion of actual positives that were correctly identified. In other words, out of all the actual positive cases, 80 plus 20 equals 100, my model correctly identified 80. So my sensitivity is 80/100ths equals 0.8 or 80%. I'm calculating the likelihood ratio for class 1, LR1. This ratio tells us how much more likely a positive test result is given a positive case, class 1, compared to given a negative case, class 0. The formula is sensitivity divided by 1 minus specificity. It is calculated as 0.8, 1 to 0.9, equals 8. That means a positive test result is 8 times more likely if the case is actually positive. Here, I am about to calculate likelihood ratios, which are essentially the ratios of probabilities that help us quantify the effect of a test result on our beliefs about an event. For example, I'll show you how to calculate LR1 and LR0. I calculate the likelihood ratio for class 0, LR0. This is similar to LR1, but now it shows how much less likely a positive test is given a negative case, class 0, compared to a positive case. The formula is 1 minus sensitivity divided by specificity. It is approximately 0.22. This means a positive test result is about 0.22 times as likely if the case is actually negative. I am starting with calculating the basic metrics sensitivity and specificity to help quantify the performance of a binary classification model. I am posing a multiple-choice question based on the calculations of LR1 and LR0. I want you to check your understanding. I see a confusion matrix. It shows how many times my model correctly and incorrectly classified things. The rows represent the actual classes, 0 and 1, and the columns represent the model's predictions, 0 and 1. For example, 90 means the model correctly predicted 90 instances of class 0. This is the main question. I need to use the confusion matrix and the prior probability of class 1. That's P1 equals 0.2. To figure out which statements about the class likelihood ratios, LRs, are true. Class likelihood ratios help me understand how much more likely a positive test result is given the positive class than given the negative class. These are the actual classes of the data points used to test the model. The model predicted class 0. 90 is true negatives, Tn, and 20 is false negatives, Fn. The model predicted class 1. 10 is false positives, Fp, and 80 is true positives, Tp. This tells me the type of problem I'm working on, classifying data into two groups, 0 and 1. The evaluation uses a confusion matrix and likelihood ratios. I'm using a confusion matrix to summarize the performance of a binary classification model. It shows how many instances were correctly and incorrectly classified. The rows represent the actual classes, and the columns represent the predicted classes. For example, 90 represents the number of actual class 0 instances that were correctly predicted as class 0. This column shows the number of instances that the model predicted as belonging to class 0, the negative class. This column shows the number of instances that the model predicted as belonging to class 1, the positive class. This row shows the actual class 0 instances. This is the number of actual class 0 instances that the model correctly classified as class 0, true negatives. This is the number of actual class 0 instances that the model incorrectly classified as class 1, false positives. This row shows the actual class 1 instances. This is the number of actual class 1 instances that the model incorrectly classified as class 0, false negatives. This is the number of actual class 1 instances that the model correctly classified as class 1, true positives. I'm presenting a multiple-choice question to check your understanding of likelihood ratios in binary classification. Let's see how well you grasp this concept. I'm providing the confusion matrix and the prior probability of class 1, P1, equals 0.2, to help you answer the multiple-choice question on likelihood ratios. Remember, P1 represents the overall probability of an instance belonging to class 1 before any prediction is made by the model. I'm evaluating a model that decides between two choices, like whether an email is spam or not. This evaluation uses a specific method, which I will discuss in the following parts. This is a table showing how many times my model correctly and incorrectly predicted each outcome. For example, it shows the number of correctly identified spam emails and incorrectly identified ham emails. This tells me that before I even look at my model's predictions, there's a 20% chance that something belongs to the group I'm interested in, the positive class, like spam emails. This is important background information because likelihood ratios are affected by the prior probabilities. This shows my model's predictions versus the actual results. Let's say 0 represents not spam, and 1 represents spam. The confusion matrix indicates the counts of true positives, true negatives, false positives, and false negatives. I'll need these values to calculate the sensitivity and specificity required for the calculations in the multiple-choice question. For example, there were 90 times the model correctly predicted non-spam. I need to check which statements about likelihood ratios are true using the confusion matrix provided. Let's see if you can solve this. This equation shows the relationship between the likelihood ratio for the positive class, LR1, the likelihood ratio for the negative class, LR0, the sensitivity, and the specificity of my model. We are checking this equation holds true. I will explain the meaning of LR1 and LR0 shortly. This statement proposes an approximate value for the likelihood ratio for the negative class. I'll calculate the actual value and see if it matches. LR0 means the likelihood ratio for class 0, which is not spam in this example. This statement suggests an approximate value for the likelihood ratio for the positive class. LR1 is the likelihood ratio for the positive class, which is spam in this case. Let's find out if this is correct. This claims that multiplying the likelihood ratios for both classes always results in 1. I will verify if this is generally true or only true under specific circumstances.